Today's topic is the adiabatic process. We know that in the adiabatic process, heat remains constant. Means there is no exchange of heat between system and surrounding. Q equal to constant. Q equal to constant means dQ equal to 0. So there is no change in the heat. Now most of the students ask about the steepness of curve, pressure and volume. So they describe the curve which is more steeper, they dub it as a adiabatic curve, and the curve which is less steeper, they dub it as isothermal curve. So this is a hypothetical question. It doesn't mean that this is a question. It is up to you. This is for the understanding. Okay. So here my aim is to teach you how to identify the adiabatic and isothermal curve, and if two adiabatics are given, then how you will decide which one is that for monoatomic and for diatomic gases. We know that here isothermal expansion is taking place. Suppose it is a adiabatic expansion taking place, and this curve is more steeper. So this is the adiabatic, this is the adiabatic, and this is less steeper. So this is the isothermal. This is for adiabatic expansion. Means pressure is decreasing and volume is increasing. So during expansion, the pressure decreases and volume increases. What about the compression? Pressure increases and volume decreases. So this is the compression. This is the compression. Means here pressure is negative in case of expansion and volume is positive in case of expansion. So if we compare this with the quadrant, in trigonometric quadrant, we have already learned in our previous classes about the quadrant. So this is, suppose this is the x-axis, this is the x prime, y-axis, y-axis. Here value is positive. We take the positive, here this value is negative. So in first quadrant, both x and y are positive. This is the first quadrant. Here angle is 0 to 90 degree. Here angle is 0 to 90 degree. In second quadrant, x is negative and y is positive. So here angle is 90 degree to 180 degree, and this is the quadrant 2. In third quadrant, x value is negative and y also negative. So negative. This is the third quadrant. Here angle is 180 to 270 degree. 270 degree. Now, if we take fourth quadrant, in fourth quadrant, x is positive and y is negative. So this is a positive, negative. This is the fourth quadrant. Here value is the 270 degree to 360 degree. Here angle is the 270 degree to 260 degree. So if we compare the expansion, here pressure decreases, means pressure is negative. Suppose pressure y axis, and volume is on the x axis. Here pressure is, in case of expansion, pressure is negative and volume is positive. So pressure negative means y negative and x is positive, means this is the fourth quadrant. Here x equal to volume, y equal to pressure. So x positive and y negative. So this is the fourth quadrant. Now if we take, here question is, if there are two angles theta 1 30 degree, theta 2 45 degree, in case of reversible adiabatic expansion and adiabatic compression, which angle satisfy adiabatic expansion and adiabatic compression? Now if adiabatic expansion is taking place, it depicts that theta 1 is 30 degree, means 360 degree minus theta 1 and 360 degree minus theta 2. So what will be the value? So now we know that we take generally, in case of slope, we generally use tan theta. So if we take tan theta here and tan theta here, so if this will be minus tan theta 1, this will be minus tan theta 2. Here theta 1 is 30 degree, so its value will be minus 1 upon root 3. Here theta 1 equal 45 degree, so its value will be 1, minus 1. So minus this value will be minus 0.57 and this value will be minus 1. So here we see theta 2 slope in the case of theta 2 means 45 degree more negative. So if slope will be more negative, then that will be adiabatic, and the slope which is lesser than will be dubbed as isothermal. Means if we plot a curve like this, and here this and this one is suppose this is A, this is B. Here A is less steeper than B, so B will be adiabatic. So theta 1 will be for this, isothermal, and theta 2 value is 45 degree, so will be for adiabatic process. Now take this example. Here this and this. Suppose this is A, this is B. So A will be isothermal here, more steeper. So theta 2. So this will be theta 2, means this will be theta 2 and this will be for theta 1. Now if we take the example of adiabatic compression. In case of adiabatic compression, pressure increases, volume decreases. Means pressure is positive and volume is negative. Means suppose this is pressure and this is volume. So this will be in the second quadrant. So positive, negative. Sorry, this is volume is on x-axis and pressure on y-axis. So this will be negative, positive. Means theta 1 here will be what? 90 plus theta 1 means 90 degree plus 30, 120 degree. 90 plus theta 2 means 90 plus 45 equal to 135 degree. 135 degree. Here theta will be 120 degree, 135 degree. We know that tan 180 degree minus theta equal to minus tan theta. So if we, here angle will be 120, 135 degree. So if we take for 120 degree, so tan 180 degree minus 60 equal to minus tan 60 degree. This is for 120 degree. So this value will be minus under root 3 equal to minus 1.732. In the case of 135 degrees, means tan 180 degree minus 45 equal to minus 45 degree equal to minus 1. So this will be minus 1. So in this case, you see that 120 degree angle means theta 1 that was theta 1 was 120 degree. So theta 1 describe this theta 1. This one describe adiabatic process, and theta 2 describe isothermal process. So here we see we get the opposite result. In case of adiabatic expansion, theta 1, theta 2 describe adiabatic curve, and theta 1 describe isothermal curve. But in adiabatic compression, theta 1 describe adiabatic process and theta 2 describe isothermal process. So we know that the slope is more negative in case of adiabatic than isothermal process. Let us see how. We know that PV relation equal to K in the case of isothermal process. So suppose we take the isothermal process. So if we differentiate this equation, we get dPV equal to dK. So it will be PdV plus VdP equal to 0, or VdP equal to minus PdV, or dP upon dV equal to minus PV. So here we see this is the PV. So slope will be dP upon dt, slope will be minus P upon V. If we take the adiabatic process, we know that PV gamma equal to K. PV gamma equal to K. In adiabatic process, PV gamma equal to K. This is for adiabatic process. So if we differentiate this, PV gamma equal to dk. So this will be P gamma V gamma minus 1 dV plus V gamma dP equal to 0, or V gamma dP equal to minus P gamma V gamma minus 1 dV, or dP upon dV equal to minus P gamma V gamma minus 1 dV upon V gamma. Here we see that dP upon dV will be what? Minus P V gamma into V inverse dV upon V gamma. Here V gamma cancel out, so we get dP upon dV equal to minus gamma P upon V. So here we see that dP upon dV is gamma times more than P upon V. So this is for adiabatic process. Here gamma comes upon PV. So in the case of isothermal process dP upon dV equal to minus P upon V for isothermal, dP upon dV equal to minus gamma P upon V for adiabatic process. Now here we see some concepts of the adiabatic process, Here we know that in case of adiabatic process, no exchange of heat between system and surroundings. So from first of thermodynamic delta U equal to Q plus W. Here heat constant. So for infinitesimal change, du equal to dq plus dw. So here dq is 0, so du equal to dw in the case of adiabatic process. Because here for adiabatic process dq equal to 0, therefore du equal to dw. Suppose we take 1 mole of an ideal gas, and 1 mole of ideal gas is expanding. So if 1 mole of ideal gas is expanding, so in that case dw will be minus pdv. Here work is done by the system. So for 1 mole of the gas, P equal to minus pdv. Therefore du equal to minus pdv. Here work is done on the expense of internal energy. Here internal energy decreases, therefore temperature decreases. In the case of isothermal process, there is no change in temperature, and that temperature is maintained by exchange of heat between system and surrounding. But in the case of adiabatic process, there is no exchange of heat between system and surrounding. Therefore, temperature decreases when gas expands, that is system work is done by the system. So here du equal to minus pdv. We know that du equal to cv dt. Okay, so change in internal is equal to cv dt. So we can write cv dt equal to minus pdv. Actually this is the CVM, molar heat capacity at constant volume, molar heat capacity at constant volume. So we know that PV equal to RT, or 1 mole of the gas, so P equal to RT upon V. So we can write CV dt equal to minus RT upon V into dV, or CV m molar heat capacity at constant volume dt upon T equal to minus R dV upon V. So if we integrate the Aero equation between proper limit, so here CVm is constant, keeping constant this, so this will become T1 to T2 dt upon T equal to minus R V1 to V2 dV upon V. So here we get CVm ln T T2 T1 equal to minus R ln V V2 V1, or CVm ln T2 upon T1 equal to minus R ln V2 upon V1. So this is a very important relation. Now we know that Cp m minus Cvm equal to R for 1 mole of ideal gas, and Cpm upon Cvm equal to gamma. So we are well acquainted with this relation. Now if we use this relation here, Cvm ln T2 upon T1 equal to minus Cp minus Cp m minus Cvm ln V2 upon V1, or ln T2 upon T1 equal to minus Cpm upon Cvm plus Cvm upon Cvm. So if we have opened here the bracket, so our ln, or we can also write here minus sign here and put this like this. So ln V2 upon V1. So here we get ln T2 upon T1 equal to minus gamma minus 1 ln V2 upon V1, or ln T2 upon T1 equal to gamma minus 1 ln V1 upon V2. Here we make V1 as numerator and V2 as denominator, so negative sign minus. Or we can write ln T2 upon T1 equal to ln V1 upon V2 to the power gamma minus 1, or T2 upon T1 equal to V1 upon V2 to the power gamma minus 1. Here we can easily derive T2 V2 gamma minus 1 equal to T1 V1 gamma minus 1. This is a very important relation. So here we can conclude TV gamma minus 1 equal to constant. So this is a very important relation. So TV gamma minus 1 equal to K. Now we know that we know that T2 upon T1 equal to T2 upon T1 equal to V1 upon V2 gamma minus 1. And we also know that from the ideal gas equation P1 V1 upon T1 equal to P2 V2 upon T2. Therefore, we can write T2 upon T1 equal to P2 V2 upon V1. So, if we put T2 upon T1, this value in this equation, so we can write P2 V2 upon P1 V1 equal to V1 V2 gamma minus 1. Now we can also write this here P2 V2 upon P1 V1 equal to V1 gamma minus 1 divided by V1 gamma minus 1 divided by V2 gamma minus 1, or P2 V2 gamma minus 1 equal to P1 V1 gamma minus 1. So here P2 V2 gamma or V2 inverse equal to P1 V1 gamma V1 inverse. Here V1 cancel out, V2 inverse cancel out. So here we get P2 V2 gamma equal to P1 V1 gamma. Very important relation. And here we can prove PV gamma equal to constant or PV gamma equal to K. So these are very important relations. There are two relations. That relation is TV gamma minus 1 equal to constant and PV gamma equal to constant. So these are very important relations which are generally asked in the examination. Now, if we want to prove some relation, other relation, if we want to prove some other relation, so if here we write PV and RT. Here, if we want to prove PV and RT upon T to the power gamma equal to constant. So we can here conclude P T to the power gamma P inverse equal to, no, this is not correct. So this is not correct. So here TV gamma minus 1 equal to K. Now if we want to find another relation of this equation, so how to find another relation? Before that we know some other relation. If we use this equation to know the work done in adiabatic process, after that I will tell you what is the relation between the other, means T proportional to B to the power 1 minus gamma and P proportional to T gamma upon gamma minus 1, and there is another relation T proportional to P to the power gamma minus 1 upon gamma. So these are the very important relations which you must know. Before that, before deriving this equation, let us know what is the work done in the case of the adiabatic process. So if we want to prove the work done in the adiabatic process, we know that delta du equal to dq plus dw, and here du equal to dw. Here because dq equal to 0 in the case of the adiabatic process. So here dw is the minus P dV if we take the expansion work. So this will be minus P dV. And we know that from the equation PV to the power gamma equal to K, P equal to K, V to the power minus gamma. So if we put this value dW equal to minus K V to the power minus gamma dV. So if we wanted to know the work done in this process, so W equal to integration minus K V to the power minus gamma dV. Now we have to integrate this equation. So in order to integrate this equation, let us do some more calculation. What is the calculation? Let us see. Here W equal to integration minus K V to the power minus gamma dV. So if you integrate this equation, here we get, suppose the lower limit is V1, upper limit is V2. So we get here minus K V to the power minus gamma plus 1 minus gamma plus 1 V2 V1, or W equal to minus K V2 1 minus gamma